All right, now we're going to move on to 6.5.2. We're going to start talking about things dropped from tops of buildings, things launched in the air, things thrown into the air. So anything that's like something flying through the air is going to kind of be our focus for the next week or so. So we're going to start here. A rock is dropped from the top floor of a 500-foot building. A camera captures the distance the rock traveled in feet after each second. So the question we want to answer is how far will the rock have fallen after 6 seconds? And we want to show our reasoning. So I'm going to zoom in here and I'm going to look at the position of the rock after 0 seconds. Obviously, we're still holding the rock and it hasn't fallen at all. Now we let go. As 1 second goes by, it is going to travel 16 feet. And then after 2 seconds, it's going to go 64 total feet. After 3 seconds, it has fallen 144, 4 seconds, 5 seconds, and so on. Now, when I look at these values, I notice that they are very similar to the values that we had in a table at our warm-up. So what I'd like to do is I'd like to go back and look at the values in the table from the warm-up. And remember, we talked about how this relationship is definitely not linear because it does not have a constant rate of change or a constant first difference, but it is quadratic. It has a constant second difference. Now, the question we're asked is how far will it have fallen after 6 seconds? Well, to do that, what we need to do is we need to notice that from this constant first difference, or from this first difference of 144, I know I'm going to add 32. Okay, so I'm going to go to my calculator and I'm going to find what is 144 plus 32. And I end up with 176. So I know for a fact that my first difference here is going to be 176. Now, that's not how far it's fallen. To figure out how far it's fallen after 6 seconds, remember, we need to find from 400, we need to add 176. So we'll go back to the calculator. From 176, we're going to add another 400. So 400 plus 176. And that'll tell us that the rock has fallen, or should fall, 576 feet. And that's after 6 seconds. Okay, so we come down here and we look at our situation, and we know that the rock should fall 576 feet. However, notice the building is only 500 feet tall. Is only 500 feet. Therefore, the rock will fall 500 feet after 6 seconds. It's only going to travel that total distance of 500 feet. Okay, now Jada was working on this problem, and Jada noticed the distances fallen are all multiples of 16. So this is kind of what Jada wrote down. She noticed the first distance was 16, the second was 64, right? So these in yellow are the distances fallen, right? And she notices that if she divides all of those by 16, she ends up with a quotient of these numbers, 1, 4, 9, 16, 25. She recognizes that 1, 4, 9, 16, and 25 is simply 1, 2, 3, 4, 5 squared. So we're going to use Jada's observation to predict the distance fallen after 7 seconds. Well, we can take this information that Jada worked on, and we know that it should be 16 times the number of seconds, which is 7, squared. And if we go to our calculator and we do 16 times 7 squared, 16 times 7 squared, notice I just type it right into the calculator, hit enter, and I end up with 784. Okay, so after 7 seconds, if the building was tall enough to allow it, it would fall 784 feet. Okay, now what we want to do is we want to write an equation with d representing the distance dropped and t representing the amount of time that has gone by. So recognizing up here what Jada has done, okay, d is the distance that it's dropped, and what Jada figured out is I can take 16 and multiply it by whatever the time is squared, and that will give us our equation representing the distance dropped after t seconds.